Hello, good afternoon, everybody. My name is Arnau Canelles Garcia, and today I will present you this seminar about the evolution of redox processes and EOCs in a set of Mark column experiments. This will be the second part because I already did a seminar on this topic, and what we had previously were preliminary results, and right now, today, we are almost finished in this project and in this paper, and I will present you the last steps that we are doing. So without further ado, first things first, for those of you who do not know what I've been working on or what is going on about all this, first, this project was about a set of column experiments about 30 centimeters long that tried to simulate a recharge system. And we wanted to test if these columns had different compositions of compost or sand. How did this affect in the degradation of generical nutrients or emerging organic contaminants? That's the meaning of EOCs, these emerging organic contaminants. Mainly what we considered in these cases were the cycles of carbon and nitrogen for the nutrients, and for the emerging organic contaminants, we'll see the 5 contaminants that have been taken into consideration. But first things first, the processes from the nutrients perspectives, mainly nitrogen and carbon, as I have already said, were nitrification, organic matter degradation due to aerobic processes, denitrification, and DNRA, okay? So the thing is that we wanted to check if in these columns, these processes that naturally occur to degrade these nutrients, what effects or what conditions happened in these columns that change these dynamics. We wanted to check if a column had more or less compost, if these processes were changed due to that. So we had one column with 0 compost, another column with 10% volume of compost mixed with the sand, and another column with 50% compost mixed with the sand. So we want to check if each of these columns had these processes and how important were they in each of these columns. So here in this slide, you can see the main processes and a summary of what we could expect in theory. So if we continue from the conceptual model from before, we had this kind of, I don't want to go into further detail in this table, but this was the main numerical table that we used for these processes. As you can see, the numbers are not the same from the previous slide. And this is because we took into consideration here the percentages and the yield of the different bacterial population. So this is why the numbers are kind of a bit weird, because we took into consideration the yield of the microorganisms, both in their growth and both in their degradation and in their metabolic processes. In this table, we will not comment in detail all the processes that are happening, but what I want to say is that for each and every one of these processes, we took into account monotype kinetic, and we considered for each one of these main nutrients that each process depended on the concentrations that we had and the bacterial population that was present in these processes. For example, in the case of nitrification, we can see that we have to take into account the presence of ammonia and the saturation dynamics that we have, the presence of oxygen, because it's dependent on the oxygen, but also the excuse me, but also the bacteria autotrophic that depend on this nitrification, and including the nitrate inhibition process. So this example shows what we took into consideration for this process, and it somewhat appears the same for all the processes present. In some others, we take into consideration other processes and other nutrients, but in general, this is the dynamic that we can see. And all this was included in our numerical code, which will show the results that we had previously. So this was the breakthrough curves that we had for the 3 kinds of columns that we had. There is a mistake in this. Oh, sorry, there was not a mistake. I thought it was 10% sand. So we can see here 100% sand, 10% compost, and 50% compost. And we see the dynamics of these 4 nutrients and of these 3 nutrients and oxygen, how they vary alongside time in the breakthrough curve. So we can see that in some cases we lack a bit of data because in the sampling that we had in Denmark, There were some cases that we did not have sampling from the beginning of the data. We had some mistakes, but in general, what we can see is that the fitting of the data is acceptable in some cases. And what we can also see is that we have a very sharp increases or decreases of these concentrations. And this was because during the experiment, there were manual changes on the inflow concentration. The changes, is if I can recall correctly, were at days 19, 29, and 49. There were like 3 or 4 changes in input concentrations for nutrients. So this is why we can see these sharp increases and decreases. It's not because numerical instabilities, it's because there are manual changes in the concentration, and these changes they occurred instantaneously. So it was like the first 10 days or whatever days, we had one concentration, and then at the 10th day there was a sudden change in the concentration, and that's why we see this sharp increase or decrease in the concentrations. So this is just for you to know it and take into consideration. This happened in nutrients, but also in emerging organic contaminants. So we will see somewhat the same pattern in the contaminants, but we will see later. In the case of the emerging organic contaminants, we took into consideration 5 of them, which were the benzophenone 3 or BP3, the carbamazepine, sulfamethoxazole, paracetamol, and the uron. We have here some of the main information that we can see about them, about this, the partition coefficients, the pKa, the solubility, their molecular weight. This is just for have a general picture of the data that we can have. But what we can see is that compounds with higher solubility would be expected to have more absorption, and as we will see, this pattern is shown in the further data that we will see. So this is just here more data about what we expected, that we have these emerging organic contaminants that whenever they are mixed with water, there is a certain tendency of being ionized. And this is also a process that we take into consideration. And these ionized compounds usually are easier to degrade or to sort than the parent compounds. So this is also another kind of information that we took into consideration for the emerging organic contaminants models. And again, this kind of ionization depends on the pH. So depending on the pH that we are working in our columns, we will see that these different emerging organic contaminants are present in a kind of more ionized, neutral, or in different kinds of ionized way or neutral. So we'll have to take that into consideration. The working pHs that we had in our column experiments were between 6 and 8, maybe 6 and 9 in some cases, depending on the depth of the column and the kind of compost that we had. But as we can see, some of these compounds are present in this working range, and some others are not. So what happens with all this? What we can define about this kind of protonation or ionization of compounds, we can define kind of a fraction or a ratio between the neutral compound and the ionized form. This will serve us in order to define the transformation or maybe degradation or absorption of these compounds. And this parameter, this alpha, it's defined by the acidity or basicity of the groups that can be attached or not to these compounds. So another thing that we'll take into consideration is that for the emerging organic contaminants, they will be mainly sorbed in the organic matter fraction that we have in our column experiments. This is completely opposite. This can be opposite to the fact that also in our columns we have sand. This sand, mainly silica sand, can be somewhat considered as non-sorbent. So this is kind of a filling for our column. In this case, what we have hypothesized and we saw in the literature is that this sorption can occur in these complexes that happen in the organic matter or maybe in the biofilm, which we'll talk into that later. But it will also make the point that these organic compounds, whenever they are in this neutral form, they are not significantly dissolved, and therefore cannot be that significantly sorbed or degraded. The fact that this occurs makes us realize and do a constant that will define this kind of sorption related to this partition coefficient and the amount of organic matter that we have in our subset of columns. This K sub D, which will define the amount or the tendency of being sorbed of these organic compounds. This kind of KD will be what we will further use in our numerical models to define this sorption. But it's not only because of this organic sorption that we have some kind of processes in this way. We have also other kind of processes that affect our contaminants, in this case. Electrostatic iterations, exchange with ligands, pH, ionic strength. All this is also taken into consideration in our model, which is based on freq C. This is why we take into consideration all these processes, because we suppose a biochemical model based on freq C. We put the different patterns and parameters into this model, and then with the APHT3D, we make this model flow and transport and degrade itself alongside time and space. So considering all these iterations, we define this KD based on all these different parameters to define this pattern, this parameter. This parameter can sometimes be referred in the freq C database as log K. So this is the different parameters and the different characteristics that define this sorption, this reaction between the emerging organic contaminant, the organic matter, and the complex made between those two elements. And the tendency, we can define the tendency between being in this ionized way or this complex way or the initial way. But this was made in the freq C as an equilibrium. As we can see, this is mainly some sort of equilibrium. But in some cases, we found that this equilibrium was not good enough to fit our data. And we had to define some sort of kinetic sorption, which was included in the numerical model. And what this defines is that we have this aqueous concentration and the relationship between this solution in the liquid and the solution that is sorbed in the solid, which is some kind of what we see here, but with one issue that it's present. That this, in order to, as it is kinetic, we can define some of these patterns and parameters, and we had to define one big important consideration, and that was that the desorption and the sorption of these emerging organic contaminants did not occur in the same manner or in the same proportion. We saw this, and we will see this in the graphs from now on, that we saw that there was some sorption in some of these compounds, but the desorption of these compounds was not at the same level or speed than this sorption. And this was shown because we had quite a big sorption at the beginning, but at the end there was not desorption. The concentrations did not increase from the inlet data, which this model, the equilibrium model, failed to do so. So that's why we needed to go into this kinetic sorption to define that the desorption was not as strong as the initial sorption. So apart from this sorption, we defined as well the degradation of these compounds. Some of them, not all of them are degraded, as we will find from now on, but we considered some kind of first order degradation, and also a first order degradation that was coupled with the biogeochemical processes that were defined in the nutrient cycle, and also some sort of lag phase or activation phase for the bacteria. So as we can see, this would be the initial way to see these processes, this first order, but we wanted to go further and define this first order coupled with the biochemical cycle and some sort of lag phase and activation phase of this bacteria. So in summary, what we can see is that the models present or the results present were divided into two main kind of of processes: the sorption process and the biodegradation process. We had different models to test the different kinds of sorption and degradations that were tested to finally get to the end data. And basically, we compared the kinetic sorption versus the equilibrium sorption. And in biodegradation, we compared the non-degradation with first-order degradation and kinetic degradation coupled to, to geochemistry. So we will see all these models now in a kind of summary to see what was the better model to fit our data. So here in these graphs, we see quite a lot of things. So don't worry, we'll break through them. First, we have the three kinds of columns with 0% compost, 10% compost, and 50% compost. So far, so good. The different kinds of emerging organic contaminants that we have, which have their concentrations in micromoles per liter, and we have also the rate of the geochemical processes. Let's go further into that. We can see in these graphs different kind of data. The black dots are the input concentration, the inlet concentration. Okay. The red dots are the outlet concentrations. So these ones are the ones that we want to match in these breakthrough curves. And then we can also see various things. First, we have a blue line, a blue solid line, which is the output concentration if there were no processes. So it would be some kind of conservative transport model. So we can see that the blue line fits the black dots perfectly. So far we're good there. Fear not that if it doesn't fit perfectly, there is some sort of error in the data. So that's why we account for that. But we also see in these graphs the filling, the space, the let me say it, the different colors and patterns that are shown in this solid wall of the graph is the ratio, the rate of the geochemical reactions that occur in our model, and we wanted to see if these geochemical reactions had any kind of effect in our emerging organic contaminants. So as we can see here, the pink solid wall, it's for organic matter degradation. Both yellow fillings are for nitrification, one step and the second step. And the two green solid fillings are for denitrification. So what we can see is that in the different steps of the model, at the final point, so these solid fillings are for the last point of our model at the breakthrough. We can see what is happening in this geochemical model and if it has any sort of relationship with the different emerging organic contaminants. So what we had here is that all these fillings, all this data. And then the two final things that we can see is that we have this dashed red line and this solid red line, which are the two models that we want to compare. In this case, for the sorption. So the red solid line would be the kinetic sorption, and the dashed red line would be the equilibrium sorption. So first things first, as we can see in the case of paracetamol, the sorption that we tried to fit was not good on the data, was not fitting good on the data, and therefore both in the literature and both on our mathematical testing, we could not make this paracetamol be sorbed and follow the tendency of the data. So therefore, this is not considered in this dynamics. Same goes for sulfamethoxazole. As we can see, the data seems not to follow this sorption dynamic. However, when we go into the BP3 or BPN, as we can see here, the sorption dynamics start to fit better the data. First, we can see this kind of equilibrium sorption, which will be kind of retardation coefficient that defines that the peak concentration of the data is further into time. So this will be the classic equilibrium, but the kinetic one shows that there is some sort of a different approach on that. And we needed this equilibrium with this kinetic equilibrium because On the dashed line, we see that there is some sort of desorption or retardation coefficient that shows that we should have higher concentrations in this model. But the reality is that the data, these red dots, are always very low, and therefore this could not be this kind of retardation coefficient that we have this this presence, this height, this peak over here. So we needed this kinetic equilibrium to further define the fitting of this data, which is also the same that we showed for the other compounds, both of diuron and carbamazepine. But the thing is that we also saw that there was other things needed for the fitting of the data that we will see in these results, including degradation. As you can see, both paracetamol and sulfamethoxazole include this degradation that there was not included before. And as we can see now, the fitting of the data is much better than before. We see that the effect of the addition of compost is significant compared to the previous model. But it can also be seen that the BP3 or BPN, when included the kinetic absorption from before and the degradation from now, the fitting is much better. However, we had some sort of technical, I would say issue, but it was part of the sampling of the data, is that in some points of time, it can mainly be seen at diuron and carbamazepine. There are like these big steps over here, as you can see, both between the days 9 and 20 and 40 and 60 or 50 something. This was because at some points in our column experiments, there was the need to take solid samples of the column. And when we took these samples, the column was, the inflow of the column was cut, the column was drained, and then the solid sample was taken. And this implied some sort of effect in these dynamics of both sorption or degradation of these compounds. So we took that into consideration. And that's why we see sometimes these big steps over here, not only because there are changes in the geochemical model, but also because there are changes in the sampling model. So as you can see in these final models, the red solid lines, the fitting is much better in this sense, because in this case, for both diuron and carbamazepine, which are mainly related to sorption, what we are seeing here is that, okay, this drainage of the column implied some sort of effect in the sorption capabilities of the column, enhancing them, and therefore reducing the liquid concentrations of these compounds, as we can see here. And this was the reason, or the final straw, to make the model fit, because at the beginning we couldn't find the reason why. And that's why we have some sort of these dashed lines, which do not fit that great. But the solid lines, which included this drainage effect, are able to see that there are some different processes occurring in between these two times. And that's what we use to finally fit the model to the data. So in summary, what we can see here is that some emerging organic contaminants, the case of diuron and carbamazepine, are mainly related to sorption, both in literature as what we can see in the data. The BP3 emerging organic contaminant was related to both of them, sorption and degradation. And both paracetamol and sulfamethoxazole were observed to be mainly related to degradation dynamics. In the case of paracetamol, mainly to aerobic processes, and in the case of sulfamethoxazole, were mainly related to the nitrification processes, which is also backed from the literature. The other thing that can or might have some sort of effect in these columns is the biofilm concentrations and the bacterial population. The bacterial population is taken into account in the model. However, it is taken into account in the nutrient cycle, but it's not fully taken into account for the emerging organic contaminants, in the sense that these emerging contaminants are shown to be more degraded or more sorbed the more compost we have. But it is unsure if it is because of the higher compost or the higher compost that caused higher bacteria presence and higher biofilm presence. This is a thing that needs to be, that is further work needs to be done in that sense, because we see the effect, we have different answers to that, but we don't have a final explanation because of this. So this is further work to be done to see if there is a clear relationship or a numerical relationship of this biofilm or bacterial enhancement to this degradation of compounds. We see it. We somehow are able to define it in some way, but we are not able to fully transform into a numerical model this increase or this variable of biofilm. So in order to sum up and conclude this seminar, we see that there are some emerging organic contaminants that are significantly affected by the biogeochemical cycles, mainly paracetamol and sulfonataxothol, that depend on the nitrification and denitrification processes are affected. Their transformation and degradation is affected. We also saw that the kinetic absorption was better in our case than the equilibrium, mainly because of the fact that we had desorption or not in the same way. In the case of equilibrium, we had the same tendency to sorb than to desorb. But for the kinetic absorption, we could define that desorption was harder than sorption. We also saw that this, especially for these recalcitrant compounds, some sort of lag phase, it's very useful to define the transformation of these compounds, which is also stated in the literature, but it was also reaffirmed in this model. And it was also seen that if we have more compost to these columns, we had more reduction of these EOCs at the outflow. This reduction, both depending on sorption and degradation. But the problem is that this reduction, it's dependent on the compost, on the increased population of bacteria and biofilm, and we are not entirely sure on that. We know that more compost has more bacteria, but what is the real reason that is reduced? Is it because of the compost, because of the bacteria, because of the biofilm? And we need to further test that. But without further ado, this is all I have to say right now. So thank you very much for your attention, and I will be glad to answer any questions that you have.
Okay, thank you, Arnau. I'm sorry I was a little bit late, so I couldn't.
Yeah, do not worry, Martin. It's fine. Thank you for letting me do it online. I appreciate that.
Yeah. Okay. So are there any questions? But actually, let me start with one question that I had. It is a little bit about the biofilm.
Yeah.
You said you took it into account.
Yeah.
Somehow, but could you be a little bit more specific?
What we took into account, this biofilm is in the data that we provided the model, mainly in the porosity and maybe mainly in the parameters that define the intrinsic transport and geochemical transformations.
Yeah.
But we did not take into account the biofilm in the emerging organic contaminants or the nutrients transformation. So we took it in the beginning of the model to set up the model. We say the model, okay, we have this biofilm, we have these properties, but we did not take into account the biofilm in the final numerical transformations or calculations. That's what I'm saying.
Okay, so it's only in the porosity.
Exactly. What we have in the numerical model is the number of bacteria that we have. So if we have an increased number of bacteria, we have enhanced transformations than in comparison to the lower number of bacteria. That's what I'm saying. But the thing is that we needed to further test the effect of this biofilm. Everybody talks about this biofilm. This has properties to sorb, properties to degrade. But the thing is that here we can only make a hypothesis on that, because we know that the more compost we have, the higher biofilm we have. So far, so good. But we have more bacteria as well. So what should we relate it with? The more biofilm, the more bacteria, both of them, and
Yeah, yeah,
and that is an unknown for us. So we did not want to risk it.
yeah,
We
yeah,
at this point of the model, we wanted to do the things that we knew and add the extra information that we have to say, okay, we also have this. This can have an effect, and it is stated in the discussion. But we were not sure to put it in the model because there is no. We needed further testing with this biofilm to see if we put biofilm, we have more or less degradation or not. That's what I try
yeah.
to say.
But I mean, the biofilm, is it, let's say, its volume fraction is constant, or
Okay, can you
because
repeat? Can you repeat? Because I
i- is the biofilm constant? Let's say the volume fraction is constant.
no, it is not.
It's
It
not.
is
Oh,
not.
so
It
you
is
change,
not.
it changes. Okay,
It
okay.
changes. It certainly. We saw it mainly in two ways. First, in the comparison between the beginning and the end tracer test, the changes were significant, especially in the columns with compost,
Yeah, yeah,
where there was also higher amount of bacteria. We saw it there, and we also saw it in the sampling that we had.
yeah, yeah. Okay. And but there's no diffusion from pore water to the biofilm, or
We are not sure about that. That's that.
no?
That's
But in your model.
no, there is not. There is not.
Okay, okay,
No,
okay.
we
Yeah, because
know.
I was thinking very often there is some lag between the diffusion, let's say,
Yes,
which
yes,
could
that's
also have this effect of an of let's say kinetic absorption or something.
yes, yes, yes. You're right. The problem is that this lag phase was not due to the uh, n- what showed this lag phase is that at the beginning we had very little absorption or very little degradation, let's say both cases, but at the end there was more and more and more of it.
Yeah,
So you could argue that this biofilm takes time to adapt, but the problem is that in some cases, for example, paracetamol and sulfametaxothol, um, the literature shows that there is degradation mainly, and it also shows that this kind of bacteria do not naturally take these compounds as food or carbon source. They need time to adapt to these
yeah, yeah,
concentrations. So that's why we had this kind of issue and kind of indecision in there. But I'm 100% sure that this model could include the amount of biofilm and bacteria further into it as a variable and compute it. But the other problem is that we had one unique sample of biofilm and bacteria. We had the sample at the end of the experiment. If we had samples alongside the experiment, let's say at day
yeah,
10, 30, 40, 50, and 60 and 70, it would be nice to have that.
yeah,
But we
yeah,
had
yeah,
only
yeah.
one
Okay,
one
it's
data
more
point at the end of the
difficult. Yeah,
experiment.
yeah,
We saw that there was differences between columns, but we did not see the evolution of this biofilm alongside time. That was the other issue that we have.
yeah, yeah. Okay, thank you. I don't know whether there are other questions, or maybe in the chat. Okay, I don't see other questions.
No,
So thank you, Arnaud, for your
thank you so
presentation.
much.
And thank you for the rest for your attention. Okay. Okay. Thank you. We leave it to this.
Thank you very much. Have a great day.
Have a great day.
Bye bye.
Bye bye.